Welcome to the deep dive. Today we're getting into something pretty fascinating, a cosmic object that's, well, a bit of a contradiction.
That's a good way to put it.
Yeah, on one hand, it's this amazing scientific time capsule, potentially holding the secrets to life itself, pristine stuff.
Right, the raw ingredients.
But on the other hand, it's officially flagged as a potentially hazardous object, something that, could pose a real risk down the line.
Absolutely. We're talking about 7-1955 Bennu. It's a carbonaceous asteroid discovered back in 1999.
And it's on that Century Risk Table.
It is. Its orbit gets pretty close to ours, uncomfortably close sometimes. But there's more to it. Even the name has a story.
Oh, do tell.
Well, Bennu comes from Egyptian mythology. It's this bird, like a heron, linked to the sun, creation, rebirth, that sort of thing.
Okay, interesting connection.
And the name was actually suggested by a third grader, Michael Puzio. He saw the OSIRIS-REx spacecraft's sampling arm and thought it looked like the neck and head of this Bennu bird.
No kidding. A third grader. That's brilliant. Ancient myth meets space age tech.
Exactly. And that mission, OSIRIS-REx, is really our main source for this deep dive. It was a huge undertaking.
7 years, wasn't it? Launched 2016, got there 2018.
That's right. Then that incredibly tense, brief touchdown in 2020 to grab a sample.
And the sample capsule just got back to Earth last year, September 2023. So you, listening, get the highlight reel of 7 years of exploration.
We're going to unpack what we learned about this asteroid dynamic. Dark, maybe a bit dangerous.
Let's start with what it actually looks like, its physical nature, because that seems key to everything else.
Definitely. Size-wise, it's not enormous. About 490 meters mean diameter. That's roughly 1,600 feet.
But it has that very specific shape, right? Like a spinning top.
Yeah, roughly spherical, but with this noticeable bulge, a ridge, right around its equator. Very distinctive.
But didn't initial observations get it kind of wrong?
They really did. From Earth, it looked, well, relatively smooth. Maybe a bit lumpy, but generally smooth.
And then OSIRIS-REx arrived.
And sent back these incredibly detailed images. The reality was completely different. Way, way rougher than anyone anticipated.
Oh, for how?
Covered in boulders. We're talking over 200 boulders bigger than 10 meters across. And the biggest one, a monster. 58 meters wide. It just dominates the landscape in some areas.
Wow. Okay, so not smooth at all. More like a giant pile of rocks. Which brings up the structure, doesn't it? How does something covered in huge, sharp rocks hold itself together, especially with that spinning top shape?
That's the million-dollar question, or maybe billion-dollar, considering the mission cost. The answer lies in its density, or rather its lack of density.
Density.
It's astonishingly low, about 1.190 grams per cubic centimeter.
Wait, water is 1 gram per cubic centimeter, so this is barely denser than water.
Barely. Which tells us it's not solid rock through and through. Not even close.
So what is it then?
It implies it's incredibly porous. What we call macroporosity is estimated at around 40%.
40%, so nearly half of its volume is just empty space, voids inside.
Exactly. Think of it as a loosely packed collection of rocks and dust, barely holding itself together with its own weak gravity. It's the classic definition of a rubble pile asteroid.
A rubble pile. Okay, so it's not one solid body, just a collection of bits.
Precisely. And this loose structure led to one of the most surprising moments of the entire mission, the sample collection itself.
Yes, the famous ball pit moment.
That comparison really stuck, didn't it? The surface regolith, the loose top layer, was just incredibly soft, unconsolidated.
How soft are we talking?
So soft that the mission team calculated the spacecraft actually punched down into the surface quite a bit during that brief contact. They said OSIRIS-REx would have sunk into Bennu had it not fired its thrusters to back away immediately.
Wow, so it didn't really land. It sort of bounced off this cosmic pillow.
Kind of, yeah, like landing in a giant pit full of plastic balls. Yeah. Very little resistance, which is just mind-boggling for something that size.
It really is this fragile, porous giant, and yet it's also considered potentially hazardous. That seems like another contradiction. How can something so loosely packed be a threat?
Well, its internal structure doesn't stop its orbit from bringing it near Earth. And its dynamics are really complex. That brings us to the second part, the forces acting on it.
It's not just passively orbiting, is it?
Not at all. Bennu is what we call an active asteroid. OSIRIS-REx actually observed it spitting out particles. Plumes of dust and even small rocks, up to 10 centimeters across, were seen leaving the surface.
Whoa, what causes that?
There are a couple of leading ideas. One is thermal fracturing. The temperature swings between day and night on Bennu are extreme. That constant heating and cooling can crack the surface rocks, causing bits to break off.
Makes sense, like rocks cracking in a desert on Earth, but, in space. What's the other idea?
It likely relates to the water we know is locked inside Bennu's minerals.
Right. You mentioned water earlier.
Yes, it contains hydrated minerals, things like phyllosilicates. These formed when liquid water interacted with rock on Bennu's much larger parent body billions of years ago.
So there's water ice or water molecules trapped in the rock.
Essentially, yes. And when the sun heats these minerals, the water can be released as vapor. This outgassing can act like tiny jets, pushing surface material away.
So it's cracking under the temperature swings and venting steam, basically, shedding its skin.
Pretty much. And all this heating and cooling, especially the uneven way it happens, leads directly to the biggest factor influencing its orbit long term, the Yarkovsky effect.
Right, the Yarkovsky effect. This sounds subtle, but it's crucial, isn't it? Explain how this works.
Okay, so imagine Bennu rotating. The side facing the sun heats up. As that heated side rotates into darkness, it radiates that heat back out into space as infrared light.
Like a hot pavement cooling down after sunset.
Exactly. But that radiated heat carries a tiny amount of momentum. It acts like a minuscule continuous thrust pushing the asteroid. Because the heating and cooling isn't perfectly even across the whole surface, this push isn't random. It nudges the asteroid consistently in one direction over time.
And it's tiny, but it adds up.
It adds up significantly.
Huh.
For Bennu, this effect causes its average distance from the sun, its semi-major axis, to drift by about 284 meters every single year.
284 meters a year, that's huge on an astronomical scale. That makes predicting its exact path really tricky long term.
Incredibly tricky. And there's another twist. The Yarkovsky effect is also changing its rotation speed. It's causing Bennu to spin slightly faster over time. The rotation period is decreasing by about 1 second every century.
So it's drifting and speeding up its spin. No wonder NASA wanted to study it up close. Measuring that effect precisely is vital for planetary defense, right? To predict where it and others like it will actually be.
That was a major reason for choosing Bennu, absolutely. It being potentially hazardous wasn't just a coincidence, it was part of the point. We needed to understand these subtle forces better.
So let's talk about that hazard assessment. Now that OSIRIS-REx has helped refine the orbit and the Yarkovsky measurements, how serious is the risk?
Well, the calculations show a cumulative probability of Bennu hitting Earth between the years 2178 and 2290. That cumulative chance is about 1 in 3,750.
Okay, still low odds overall, but not zero. Is there a specific date that stands out?
Yes, the single highest probability impact date is calculated to be September 24th, 2182. The chance on that specific day is about 1 in 2,700.
And if that unlikely event did happen, what kind of impact are we talking about?
The energy release would be immense, estimated at 1,200 megatons of TNT equivalent.
1,200 megatons. How does that compare to something we know?
Well, the Tunguska event in Siberia in 1908, which flattened a huge area of forest, is estimated at maybe 3 to 5 megatons. So Bennu would be hundreds of times more powerful. It's a civilization-altering scale of impact, though not an extinction-level event like the dinosaur killer.
That's sobering. But you mentioned the risk depends on something happening much sooner, right? In 2135.
That's right. In 2135, Bennu makes a close but safe flyby of Earth, passing about 203,000 kilometers away. That's closer than the moon.
Still sounds pretty far. Why is that flyby so critical for the 2182 risk?
Because of gravity, specifically Earth's gravity. During that close approach, if Bennu passes through certain very small regions of space near Earth called gravitational keyholes, our planet's gravity will tweak its path just right.
Just right, to put it on a collision course for 2182.
Exactly. These keyholes are incredibly small zones. Some calculations suggest they could be as narrow as 5 meters wide.
5 meters, that's tiny. The width of a car determining the fate of an asteroid half a kilometer wide decades later, that really highlights the precision needed.
It absolutely does. Tiny changes now lead to huge differences later. But, looking at the really, really long-term picture might offer some perspective.
How so?
Over the next, say, 300 million years, models predict Bennu has about a 48% chance of eventually falling into the sun.
Okay, that's the most likely fate.
Then about a 26% chance of hitting Venus, and maybe a 10% chance of hitting Earth over that vast time scale.
Right.
So while the near-term risk is real and needs monitoring, we aren't its most probable final destination.
Right. Which loops us back to why we went there in the first place, not just the hazard, but the science. the chance to study this pristine, carbon-rich material.
Exactly, that was the primary scientific driver. Finding the origins of water and organic molecules in the solar system, things that could have seeded life on Earth.
And they specifically targeted the Nightingale site for the sample grab because it looked different, right? Redder.
Yeah, spectrally redder, which often suggests fresher, less space-weathered material, closer to its original state. And even before the sample came back, the instruments on OSIRIS-REx confirmed Bennu was water-rich.
Finding those hydrated minerals you mentioned, the phyllosilicates and magnetite, evidence of past liquid water.
Correct. Strong evidence that liquid water was present on Bennu's parent body, wherever that was, billions of years ago. The estimates for water content locked-in minerals are around 1% by weight minimum, maybe up to over 6% potentially.
And then the sample itself arrived. How much did they get?
Way more than planned. The goal was 60 grams. They ended up with 121.6 grams, a huge success.
Double the goal. And the material itself, you said, very dark.
Extremely dark. It visually resembles those very rare CI chondrite meteorites, which are considered among the most primitive materials we have. But Bennu's sample is even more pristine, obviously, having not gone through Earth's atmosphere.
What makes it stand out from those meteorites?
Well, besides being untouched by Earth, it has a really high carbon content, around 4.5 to 4.7% by weight. And significantly, it's packed with pre-solar grains.
Pre-solar, meaning grains that formed before our sun even existed.
That's right. Tiny specks of dust forged in other, older stars that got incorporated into our solar system as it formed. Finding lots of them confirms we're looking at incredibly old, fundamentally unchanged material from the dawn of the solar system.
Wow, okay. That really sets the stage for the biggest discoveries, particularly for astrobiology. The analysis reported early this year, 2025. What did they find in that ancient carbon-rich dust?
This is where it gets truly exciting. They found phosphate minerals, which are crucial. Phosphorus is the backbone of DNA. But the real headline was the organic compounds.
We knew asteroids had organics.
We did, but the sheer diversity and completeness found in the Bennu sample was staggering. It's like they found the whole toolkit.
Okay, give us the specifics, the building blocks of life.
They identified 14 of the 20 amino acids that life on Earth uses to build proteins. 14. These are essential for constructing complex biological machinery.
14 out of 20. That's incredible.
But wait, there's more. And this might be even bigger. They found all 5 nucleobases.
All 5. You mean adenine, guanine, cytosine, thymine.
And uracil. The A, G, C, T, and U that make up the letters of the genetic code in DNA and RNA. All 5 were present in the Bennu sample.
All of them. In pristine condition, delivered from an asteroid. That's profound. It means this dangerous rubble pile basically carried the instruction manual for life as we know it.
It strongly suggests that, yes, it shows these complex molecules, the absolute fundamental precursors for biology, weren't some fluke that only happened on Earth. They formed out there in the early solar system on asteroids like Bennu or its parent body.
Amazing. So let's recap this for you, our listener. We've looked at Bennu, this dynamic, spinning, shedding rubble pile that's slowly drifting closer thanks to the Yarkovsky effect. We studied it partly because it poses a potential, albeit small, risk to Earth way down the line around 2182.
A risk defined by tiny gravitational keyholes during a 2135 flyby.
Right. But investigating that risk led to this incredible scientific payoff. A sample twice as large as expected returned from Bennu.
And that sample contained truly ancient material, rich in carbon and water.
And crucially, it held the key ingredients for life. 14 amino acids and, remarkably, all 5 nucleobases needed for DNA and RNA.
It really ties together the 2 big goals of the mission. Planetary defense, understanding the hazard and origin science, understanding where we came from. We went to study a potential threat.
And found the building blocks of our own existence.
Precisely. And that leaves us with a really provocative thought, doesn't it? Given how packed this sample is with pre-solar grains, and the fact it contains the complete set of nucleobases, what does that really tell us?
About how common these ingredients are.
Exactly. How universally distributed are these fundamental building blocks of life throughout the solar system, maybe even the galaxy? Were they essentially everywhere, just waiting for the right conditions like those found on early Earth to assemble? That's the deeper understanding these Bennu samples are starting to unlock.